All right, guys, so we'll just pick up where we left off yesterday here. We had talked about kind of the first few points here of the of Dalton's atomic theory, but we'll just quickly start Dalton's atomic theory again because it's basically the basis for everything that we do, okay, in terms of how things behave in chemical reactions and chemical properties, physical properties, etc. Okay, so obviously Dalton said, he quoted Democritus, all elements are composed of tiny indivisible particles called atoms. Okay, atoms of the same element are identical. So every carbon atom, okay, looks the same. Every oxygen atom looks the same. Okay, but obviously carbon atoms and oxygen atoms look different from each other. Okay, because they have different numbers of protons, neutrons, and electrons. Okay, and it is this number of protons, neutrons, and electrons, mostly the protons, okay, that gives each element its physical properties. Okay, that makes it the way it is, okay, that determines its melting point, its boiling point, its color, its density, all of that kind of stuff. All of that is determined by the atomic structure, okay, of that particular atom. Everybody with me there? Okay, all right. Hey, atoms of different elements can combine with one another, and I think we said this simple whole number ratios, and I wrote down at the bottom there yesterday, okay, kind of a basic reaction, which was just, okay, hydrogen reacts with oxygen, okay, to form water. Okay, and when we do that, we notice that everything is a whole number. Okay, this little 2 here means there are how many hydrogen atoms? Yeah, it's not a trick. 2. Okay, this means that there's how many oxygen atoms? 2. Okay, and over here, well, I've got 2 hydrogen atoms, 1 oxygen atom. Okay, everything is a whole number. I can't have half an atom or a quarter of an atom, because if I do, I don't have enough protons for it to be that material anymore. All right, a quarter of an oxygen atom is something else. Okay, it's helium or something. Okay, it's just not right. All right, we can't have part of an atom. It just doesn't work that way. All right, so the simple whole number ratios basically says, okay, this is how things go together. And then that leads into point number 4 about what happens in a chemical reaction. In this chemical reaction, I am joining 2 different atoms. Okay, I'm joining them to make a new compound. There are other kinds of chemical reactions where things can be separated. Okay, they can be rearranged. Right, and I think the example I showed you was something like this. We had copper reacting with silver nitrate. Okay, and that gives us copper nitrate and silver. Okay, and I said that the alchemists would have been kind of all over a reaction like that because they would have thought it meant that they magically made copper turn into silver. Okay, which they haven't, of course. Okay, all that has happened is in this chemical reaction, some of the atoms have rearranged. Okay, they've switched places with each other. Copper switched places with silver. Okay, and what we end up with, okay, is different combinations of material. All right. Now, what that would look like to a person watching this reaction, it would look like this. Let's say you put a penny in this solution, okay, of silver nitrate, because you don't normally see silver nitrate as a solid. It's usually dissolved in water, and it's just a clear solution. If you left that overnight and had like kind of a camera taking a picture of it, let's say every 5 minutes, you would gradually see the penny starting to turn grayish silver, okay, because silver would be plating out on it as the copper and silver switch places. Now, the other thing that would happen is the solution would start turning blue, because when copper is combined with something else like nitrate, its solutions are always blue. All right, so the next day when you come in there, you're going to have this penny that looks silver, okay, and it's going to be sitting in a blue solution. When you left it, it was a copper penny sitting in a clear solution. All right, and so, you know, the alchemists would have had, you know, no way to really explain that other than they were brilliant, okay, and magic, and they possess special powers or something like that. Okay, but in the end, all it's saying here is things have switched places. They're still all in whole number ratios. There's 3 oxygens. There's 2 of these nitrate molecules, and there's 1 copper and 1 silver, same as there was on the other side. Okay, everybody with me there? All right, so big thing to remember there, okay? Atoms of one element are not changed into atoms of another by a chemical reaction, okay? That's chemistry. Alchemy says that is what happens. Alchemy says I changed copper into silver because I'm great, okay? Chemistry says these things rearrange and switch places. All right? Questions on that? Okay, important that we kind of understand the implications of the atomic theory there. All right, so it's been generally accepted that these points are all still true, okay, as far as we know. Now, obviously, the indivisible part, okay, we've proved that you can actually split the atom, but it's not a natural process, okay? Yes, some things are naturally radioactive and they break down and turn into other things, but, okay, the atoms don't just split on their own, thankfully, because that would be very bad, okay? But, yes, given the right conditions, we can split the atom. We showed you yesterday how you build a nuclear bomb and how you, use it, build a nuclear reactor and stuff like that. All right. So yes, while it's true they are divisible, they're not truly divisible by any natural means. Okay. All right. Now, because Dalton didn't have any kind of information about particles within the atom, he just said everything is made of these atoms. Okay, he didn't know that atoms were made of stuff. He just thought atoms were as small as you could get. Okay, and each element had a different atom. All right, he just said atoms look like spheres. It was a decent conclusion given what he knew. The sphere was a fairly common, naturally occurring shape. Okay, planets were spheres. Okay, stars were spheres. All these things. Spheres was a natural shape. It made sense to say that the smallest thing that makes up all matter should be a sphere. All right, everyone okay with that? All right. Now, after Dalton, people started kind of investigating a little more about how the atom worked and how what kind of things went on, right? And what people discovered is that in certain chemical reactions, electric currents could be produced. Okay? Now, the only way for an electric current to be produced while atoms are changing places and rearranging or separating and joining like Dalton said they did, was if there was some small part of them that could come off and flow through a wire as an electric current. Okay, you guys following my logic there? All right, so this kind of meant that the solid sphere model didn't fit, because the solid sphere model said an atom is this. It is a small little ball, and that's all. Okay, it doesn't have any other parts. Well, from these experiments, that's not true. Okay? It means that there is some other part on the atom that can come off and flow through a wire. So we have to modify our model of the atom. The solid sphere is clearly not correct given the results of these experiments. So J.J. Thomson came up with this idea. We'll keep the solid sphere, but we'll say that embedded in its surface, loosely, okay, not tightly, but loosely embedded in its surface, are these negative little particles called electrons. Made sense to call them that because electricity, right? So it made sense. It was a logical name. All right. Now, he said that since atoms he knew were electrically neutral, okay, he said that the big solid part is positive, and all these little negative parts, okay, are very small and they're just embedded in the surface, and that those charges balance each other out and the atom remains electrically neutral. Right? Again, it was a logical conclusion given the time, and this model was accepted for quite a while. Okay? But again, people do more experiments, they find out other things. The results of their experiments don't support this model anymore. We have to come up with something else. Okay? All right, questions on that? Okay, so J.J. Thomson's model, okay, was called the plum pudding model. I'm assuming because if you have pudding with plums in it, it looks like that. I don't know. Okay? So that's what he called it. And it was, like I say, well accepted for a significant amount of time. After this, atomic physics, not chemistry, atomic physics is really where all this stuff was discovered, really took off. All right? And people started doing all sorts of experiments with X-rays and gamma rays and bombarding things and discovering that, it's not just the solid sphere with these little electrons on it. There are other parts. There are small positive parts. And when people discovered that there were small positive parts, then they started calculating masses and figuring out that if there was only these small negative pieces and these small positive pieces, matter wasn't heavy enough to account for all the mass there was in the universe. So they said there must also be some neutrally charged particle in the nucleus that helps make up that extra mass. Okay, and that was the neutron. Okay, so this is where the idea of protons and neutrons and things like that came from, is from these experiments that said, I don't get my results. I have to be able to explain them somehow. They don't agree with this model. There's no model to explain them, so I got to come up with one. All right, and that's how science works. If you have an experiment and the results don't agree with something, either you did it wrong, okay, or you've got to think up a new model. Okay, now if you think you might have did it wrong, what should you do as a good scientist? Do it again. Okay, you don't get to come up with a model like this if you have not repeatedly shown that your results happen consistently. Okay, you can't just go, hey, look what happened. I'm brilliant. I'm coming up with a new model. If you did it one time, okay, it was probably just a fluke or you misinterpreted it. Okay, good science is repeatable. All right, and not just by you, but by other people. All right, and that's the difference between chemistry and alchemy. Okay, in alchemy, people would do something once and never tell anybody else because they didn't want the secret to get out. All right. Whereas in chemistry, if you have something happen, you tell other people about it so that they can do your experiment and see if they can repeat your results. Okay. When that happens, okay, then you can come up with your sort of new ideas, new theories or laws or whatever. All right. So there was this sort of idea. Okay, with this here, where we had still kind of clinging to that solid sphere idea, where there were pieces in the atom. Okay, and then there was more of the kind of more modern idea where there were protons and neutrons, okay, and electrons, okay, orbiting that nucleus. Okay, why does everyone think the electrons should be going around the outside? Why wouldn't they be in the middle? Right. In a reaction, electrons are lost, traded, switched, whatever. They come off and go back onto atoms very easily, whereas protons and neutrons, they never do that. All right, and people discovered that in their experiments, and so they said there's no way that electrons can be part of the main part of the atom. They have to be kind of on the periphery where they can be easily switched or lost or gained or whatever. All right. Okay. Now, the other thing that people discovered was protons and neutrons were way bigger than electrons. Okay, electrons are incredibly small. Okay, on the order of like several thousand times smaller than protons and neutrons, which are also very, very small. Okay, but by comparison, neutrons and protons are gigantic compared to electrons. Okay, so the majority of an atom's mass is those two particles, protons and neutrons. Okay. All right, so James Chadwick comes along. He discovers protons are not the only large particle in the atom. He's the one who did the math on the mass of things. Okay, when he said, when people said, well, protons have this mass and the electrons have this mass, he said, well, that doesn't work. Then everything is way too heavy. All right, so then we have to figure out that there's something else in there. Okay, and we won't go into his experiments because they're like deep atomic physics type things. But okay, suffice it to say, he's the one who came up with the idea of the neutron. Okay, it carries no charge, but is identical in mass, okay, to the proton. So they're pretty much, they look alike. If you could see them, you wouldn't be able to tell them apart. Okay, but one has a charge and the other doesn't. All right. Now, of course, later on, we don't talk about this much in Science 10, but later on it was discovered that protons and neutrons are actually made up of smaller parts. Anyone know what they are? Quarks, muons, okay, and then there's all kinds of different quarks, which you'll learn about if you take Physics 30. There's up quarks, down quarks, strange quarks. There's two others I can't remember. Okay, there's all kinds of different quarks. The atomic physics is like wacky. Okay, all right. So suffice it to say, the more we discover, the more we realize that the atom really wasn't the smallest part, okay, of matter. It's the smallest part that retains the properties of that matter, okay, but there are parts that make it up. Okay, so further to this discovery came probably the most important thing, okay, that was ever done in terms of our understanding of what the atom looks like, and that was Ernest Rutherford. Okay, he said atoms couldn't have all these particles floating around randomly. Plum pudding and solid sphere weren't accurate. Okay, there had to be something else. So he conducted an experiment. Okay, his idea was that the atom is made of mostly empty space. Okay, that yes, there's this kind of nucleus area, and that electrons kind of go around it, but the nucleus is really, really small compared to how big the atom would be if you included where all the electrons would be. All right, so imagine it's kind of like the solar system. Okay, the sun is by far the biggest thing in the solar system, but when you compare how big the solar system is to the size of the sun's pretty small. Okay, there's a lot of empty space in our solar system. So if you do that, if you look at an atom in kind of a similar way, that's what he thought. Everybody with me on that one? Okay, so what he said is, I'm going to prove this by taking a piece of foil. It was made out of gold. It wasn't made out of aluminum. Okay, he had gold foil. Okay, and he shot X-rays at it. Okay, his idea was that if atoms were really, really small, most of the X-rays would go right through the foil. Okay, and they would end up on the other side. So what he did is he took photographic film, kind of like what you would use if you got an X-ray, okay, and he put it all around this this gold foil. Right? It looked like this. So here's this piece of gold foil. Okay, here's his source of alpha particles. Okay, so alpha particles are essentially very small atoms, like helium atoms or whatever. Okay, so he's firing these at the gold foil. His idea is that all of them will come and hit over here because there's so much space between the gold atoms. Okay, alpha particles are very small compared to gold atoms. Everybody follow me so far? Okay, but what he found was a lot of those alpha particles bounced off or were deflected and went in other directions. Okay, so what he said was, all right, I'm partially right. There is a lot of empty space in the atom, but not as much as I thought. Okay, because a lot of these alpha particles hit something and bounced off. So essentially his experiment proved the nuclear model of the atom, that the atom does have a central dense nucleus surrounded by electrons, all right, because some of his alpha particles bounced back. Now, as a nuclear physicist, this was very exciting to him. Okay, he was like, he just went off his rocker and he was like, it was like shooting a shell at a big artillery shell at a piece of paper and having it bounce back at you. It was just so cool. Granted, you know, physicists get excited about different things. Okay, but that's what he said it was like. All right, and that was his experiment. So this is kind of an important step in our understanding of the atom, as Rutherford proves the existence of the nucleus. Okay, and that the nuclear model of the atom is true. Now, does that mean Rutherford was right about everything? No, it doesn't. Okay, because this is what Rutherford said the atom looked like. Okay, he said there's a nucleus and there's protons and neutrons in there, but the electrons are equally distant. All of them are the same distance from the nucleus, and they kind of just offset their orbits a few degrees, okay, and they all orbit like that, right? Which has been later proved to not be correct. Okay, questions on that so far? All right, then Niels Bohr came along, okay, in the boring world of Niels Bohr, okay, and he did a few experiments as well. His were more about what are the electrons doing? Everyone was fine with protons and neutrons are in the middle. Yeah, okay, we're good with that. Ernest Rutherford's experiment was good. But now the argument is, what are the electrons doing? Okay, because people didn't like Rutherford's kind of geometric model where all the electrons were the same distance from the atom, because it didn't explain some things. Okay, one of those things is fluorescence. Okay, how many people have like glow-in-the-dark numbers on their watch? Okay, where if you're out in the sun, then you go in the dark, the panel glows for a little while. Okay, not the battery operated one, but just glows for a little while. Okay, Rutherford's model didn't explain that very well. Okay, and Niels Bohr tried to explain it. He did somewhat, and then a guy named de Broglie came along after with a model that does explain it. What happens for those glow-in-the-dark things is sunlight imparts energy. It hits the atoms of this material. And the electrons that surround those atoms gain energy because they're getting hit by this solar energy. And when they gain energy, they move faster and they move farther away from the nucleus. Okay, everybody with me there? Right? As they gain energy, they move farther away. Now, when you go in the dark, you remove the source of energy that's given them this extra speed and move them further away. So what they do, they start losing that energy. And they give it off in the form of light. Okay, so as they fall back closer to the nucleus, they glow. All right? Plants use the same thing for photosynthesis. Okay, when sunlight strikes the leaf of a plant, some of the molecules on the chlorophyll get excited, some of the electrons, sorry, get excited and they move further away. Okay, and then that's the light reactions. When they start making sugar, they use the energy of the electrons falling back towards the nucleus, okay, to start turning carbon dioxide and water into sugar. Okay, so it's the same idea. Unfortunately, Rutherford's model didn't explain that. Okay, his didn't account for how electrons could move away and move faster and whatever. Okay, so Bohr came up with the planetary model, which said, you know, electrons are in these fixed orbits, but they can jump from one orbit to another. All right, which is somewhat true. If you took a picture of an atom, it would probably look something like this. Okay, but de Broglie came up with an even better idea. Okay, he said there's a cloud of electrons. There's no fixed orbits. Okay, electrons don't move in perfect circles. They can move in ellipses. They can zigzag. They can hop up and down. Okay, and it's been later proved through certain types of experiments involving radiation that electrons move almost randomly. Okay, throughout. Okay, this electron cloud that surrounds the nucleus. Okay, so this is the model we currently accept. Okay, de Broglie's model, okay, is called the electron cloud model. Okay, and it says that electrons can be found anywhere in this area. Where they can be found depends on the energy they possess. Okay. Okay, and that's about all we really need to know about the different models, and about de Broglie's model. All right, we'll talk a little bit more about atomic structure tomorrow. Well, probably not tomorrow, but next week. Okay, but for now, that's what we need to know about essentially the history and the development of. Okay, again, the big thing here is that we can accept something because all the data and all the experiments we've done say that it's true. Okay? But we can never prove 100% certain that that is correct. Something can always come along later that would say we have to modify what we know. All right? I'll give you another example of that process. Okay? Just as I was entering high school, they changed the way they classified all the living things on Earth. Okay? When your parents were in school, they were probably told that everything was either a plant or an animal. There were only two kingdoms, for all the life on Earth. Right? Everything could fit into there. Problem is, that's not right. And scientists refused to change the way they thought about it, even though they had evidence to prove the contrary. Right? For example, if you look at a mushroom, is a mushroom a plant or an animal? Neither. Okay? It's not a plant, but it was all fungus was put in the plant kingdom for hundreds of years, even though people knew they're not really plants. Because what don't mushrooms do that plants do? Right, they don't carry out photosynthesis. In fact, fungus, mushrooms, have a digestive process that's more similar to us. Okay? They break down other material for energy. They don't use the sun at all. Right? But they're also not animals because they don't move around and they don't have certain structures and things like that. They needed their own category. Right? Same idea went for things like amoebas and paramecium and things like that, things that live in like scummy pond water. Right? They're not really animals. They're not really plants. They kind of have characteristics of both. Okay? So they needed to be in their own group. And bacteria were another one. Bacteria were classified as plants for a long time. Bacteria don't carry out photosynthesis. They live in your body and make you sick. Okay? They help break down dead material outside and all kinds of different things. They're very useful and sometimes very harmful, but they're not plants. Okay? Nor are they animals. So people had to change the way their thinking was, and as a result, they went from a 2-kingdom system to a 5-kingdom system. Okay, to more accurately portray the different groups. Okay, but again, it's a matter of process. These results don't support this idea anymore. We got to change this idea. Okay, that's why in the scientific method, you investigate a problem by generating a hypothesis. Okay, you do an experiment to test that hypothesis. You analyze your results, and then you make a conclusion that says, my hypothesis is either supported by this or is not supported by this. Okay, and then you move on, you try a different hypothesis. Okay, most hypotheses, right or wrong, you suppose? Wrong, yeah. Okay, in good science, you should be wrong 9 times out of 10. Okay, that's how you discover things, is by being wrong. Right? You should be wrong 9 times out of 10. I'm not saying you should get the hypothesis wrong in your lab reports 9 times out of 10. We make it a little easier for you here. Okay, but in good science, that's how the process moves. Okay. This might be the solution to the problem, but it's not. Okay, well, these results might say this. Let's try that instead. Okay, that's how that scientific method process works. Okay, so structure of the atom as we currently understand it is that there is a dense, positively charged nucleus. Okay, it's positively charged because that's where the protons are, and the neutrons, but the neutrons don't have a charge, so it remains positive. Okay, and then surrounding that, okay, are the electrons, which are negative. What keeps the electrons from flying off? Partially, but what force kind of keeps them there? I mean, you can orbit, but the only reason the planets orbit the sun is because the force of gravity keeps them from flying off, right? Yeah, exactly. Electromagnetic attraction. Okay, opposites attract. The nucleus is positive, the electrons are negative, and they kind of hold together in that way. Okay, now they have to move fast enough, orbit-wise, that they don't crash. If they were to slow down, okay, enough, they would eventually crash into the nucleus. That would be bad, because that would be the end of the universe as we know it. Okay, there's a whole bunch of things that say there's this degeneracy force that keeps them from doing that, but that's all like way beyond what we're going to talk about. For now, we can just say, yes, opposites attract, and that's why they don't generally fly off. Okay? But our model does say that there is a lot of empty space in the atom. Okay? And that is true. Okay? All atoms are made of a lot of empty space. All right. Now, back to why are all the elements different from each other? Okay? And this goes back to the properties of an atom are based on the number of protons in the nucleus. Okay? So, all elements have different numbers of protons in their nucleus. Okay? Important for us to understand that. Okay? It's also important to understand that electrons, the number of electrons, has absolutely no effect on the physical properties of an element. Okay? Why is that important? Because they can lose and gain them all the time. Okay? In chemical reactions, okay, electrons are lost and gained and all kinds of things like that. So they have no effect on the physical properties, only the number of protons. Okay? Neutrons, no real effect on the properties either, which is important because it's actually been found that not all atoms of carbon are exactly the same. All atoms of carbon have exactly the same number of protons, but some atoms of carbon have different numbers of neutrons. Okay, how many people have heard of carbon dating? Okay, carbon dating is a way to determine how old certain things are, like if you find fossils and stuff like that. Okay, the way it works is that some atoms of carbon have 14 neutrons. Or sorry, have 14 particles in the nucleus, so they have more neutrons than they're supposed to. These ones are actually slightly radioactive, and they decay and break down into other stuff. Okay? The amount of this other stuff that's there can be measured, and from that you can determine how old the material is, because the rate at which carbon-14 turns into this other material is known. And so by determining how much of it is there, you can determine how old it is. Right? But again, carbon-14 and regular carbon have the same physical and chemical properties. Even though they have different numbers of neutrons, they have the same number of protons. Okay, so they have the same physical properties. Question? No? Okay. All right, so basically, big thing to remember, protons. Number of protons is what determines the properties of an atom. All right. Okay, I'm going to give you a sheet here that's got a few questions on it that I want you to answer, okay? And then we'll go through them because we got lots of time. You'll finish them easily. Okay, we'll go through them together, and then what do you suppose tomorrow's quiz will be on? Yeah, this lesson, those questions that you're going to do, okay? And will you get the quiz tonight? Yes, I will tweet it, okay? I'll put it out on Twitter tonight. So if you're not following on Twitter, you're either going to have to follow on Twitter or go to the website tonight to get that quiz, okay? All right, so make sure, guys, complete sentence answers, because you're going to need to use these answers to study from, okay? Not just for tomorrow's quiz, but there's also going to be this material, obviously, on your unit exam, and when you come back, you want your answers to make some sense, all right? So make sure that you make thorough, complete sentence answers on these. All right, guys, let's go over these here. Whether you got them all done or not, you can just follow along here. Okay, so question number 1. The idea of the atom was first proposed by whom? Okay, Democritus was the first person to come up with the idea. Why was it not accepted then? Okay, one of the reasons was Aristotle was more respected and he had the four elements idea. Okay, but what was it about the four elements idea in addition to that it was Aristotle's that made it more, desirable for everyone? Yeah, it was easier, it was simpler, and it was something they could understand and see and touch, okay, and that kind of thing. They understood that, steam was some parts air and some parts water. It made sense. Little tiny particles they couldn't see was not an acceptable idea, okay, at the time. It was much more tangible for them. Okay. All right, number 2, what elements did the Greeks believe all matter was made out of? So what were the 4 elements? Water, air, fire, earth, okay, are the 4 elements that the Greeks believed in. Okay, why was this a logical conclusion? Well, we talked about it already. It was something they understood. It was something that made sense, that they could understand that everything was a mixture of some of these things, and it was an acceptable idea that was tangible for them. Okay, during the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. They were the alchemists. Okay, what were they trying to do? Right. In fact, the real word that we're looking for here is transmute. Okay, one thing into another, like lead into gold. Okay, or find the elixir of life. Okay, things like that. They were trying to do things that are physically and chemically impossible. Okay, but in the interim, they did find out a lot of interesting things that were quite useful. Okay. 1700s, a man used the data from many experiments on matter to develop an idea on the structure of matter. Who are we looking at? Quinn? Dalton, right. Okay, and in science, most of the time it's acceptable to just use a person's last name. Okay, if you remember his first name was John, that's great, but you don't have to. So, what were the points of his theory? First point is, right, in fact, not just elements, all matter is made up of tiny, indivisible particles. Okay, so point number 1 is about, okay, tiny particles. Okay, just as a summary here, because I don't have that much room. Okay, because I write big and messy. That's why I use the smartboard. Okay, number 2, second point. Right. Okay, so elements, atoms, okay, are identical. Okay, third point. Okay, combine in whole number ratios, right? That's the big thing. Combine in whole numbers, okay, to make compounds. Okay, and the fourth point talks about kind of how that happens. They can be separated, joined, or rearranged, but they cannot turn into something else. Okay, you cannot turn carbon into oxygen, right? You cannot turn, lead into gold, things like that. All right, we probably won't get to the rest of those, but you've got them answered, okay? You can look up the rest. I will post the quiz later on this afternoon. We'll go over the quiz and we'll go over the rest of the answers tomorrow.
Jacob Strawberry.